Hi, my name's Tracy Haxton. I'm a Technical Director at Wallingford Hydrosolutions, and today we're going to talk about the FEH Rainfall Runoff Method. So, as we go into this, we're going to assume that you're familiar with the main features of FEH, which we cover in our Introduction to FEH presentation, and that you're also familiar with the FEH datasets that we cover in our FEH datasets presentation. This talk is going to just focus on the technical aspects of the rainfall runoff method. We won't really be going into detail on the software. So if you're interested in the rainfall runoff method, there are three aspects of the FEH handbook that you need to be familiar with: the supporting literature, the data sets, and primarily that's the FEH web service catchment descriptor dataset, and the software itself, ReFH. So if we look at the quick summary of the FEH methods, what we're interested in here is the rainfall runoff method. We see that back in 1999, with the development of the original FEH handbook, the rainfall runoff method was released in the micro FSR software package. This was an update of the original FSR rainfall runoff method. In 2006, ReFH1 was first released, and then in 2015 through to 2019, there are a number of updates to that methodology, which were released in ReFH2 up to ReFH2.3. So the first major change came in 2006 when ReFH1 was produced. There were significant changes to the original FSR rainfall runoff method. More calibration data was used, higher resolution soil map data was used, as in the host data set. It allowed for variation in the soil moisture capacity during the storm, and also allowed variation in the river base flow within the flood event. In 2015, this was updated and released as ReFH2. There were improved design methods for England, Wales, Northern Ireland, and a completely new design package for Scotland. It also allowed you to estimate the parameters using plot scale equations, so you didn't have to use the catchment descriptor methods. It used both the FEH 2013 DDF rainfall runoff model and the FEH 99 DDF model, and it incorporated urbanisation using the latest published methods at the time. Later on, there was a ReFH 2.2 update, and these were mainly minor changes, so I've just listed the main changes below. The next main update came in 2019 with the release of ReFH 2.3. I'm going to split the updates into two aspects. First, the software updates, the front end, and then the science updates, the back end, basically. So from the front, what we can see is, first of all, you can still use the ReFH 2.2 model. The legacy model is still there. The ReFH 2.3 model includes the use of BFI host 19. You can adjust the rainfalls to allow for climate change by a simple percentage uplift. The rainfall is no longer restricted to the 1 in 1,000 year event, and you can also import observed rainfall. In terms of the science behind the scenes, well, first of all, the model was calibrated using the revised BFI host 19 dataset. It also incorporates water balance features. So the first is through the use of the BR, the base flow recharge. This is based on a water balance assumption. We'll go into this in more detail later on. Also, the model run is segmented into sub-events, and adjustments are made to soil moisture conditions for each sub-event. And the third is that in the urban model, there's an addition of depression storage, which allows us to maintain a water balance within the urban events. In addition, there is an adjustment so that when we're estimating a rainfall profile where we're using a large number of time steps, which is not particularly applicable for fluvial application, we have now removed the incidence of the very high central rainfall values that would occur. This would particularly occur for summer events when you're using it for sort of drainage design, where you might have sort of 50 to 100 time steps. When you're using it for fluvial applications, generally you're only looking at 10 to 20 time steps anyway. So the main aspects of the rainfall runoff model is that we've got our rainfall at the beginning. This goes through a loss model, so we get our net rainfall. This is then put through a routing model, which uses the unit hydrograph method. That direct runoff is then used to control the base flow component. We add all these together and we get our flood hydrograph. If you've got gauge data, you can calibrate those parameters based on observed data. If it's ungauged, you can estimate those parameters from catchment descriptors. And this method is applied within the ReFH software. So if we look at in more detail at that rural model structure, it's represented here. We can see we've got two main aspects. The top bit here is controlling the loss and the routing, the direct runoff, and the bottom bit is the base flow. So you can see there's no direct links between those two aspects. So what are the advantages and disadvantages of this simple structure? Well, first of all, because it is so simple, we can calibrate it fairly easily using a minimal number of events if we've got gauge data. And because it is simple, it also allows us to estimate our parameters using regionalised models. There are two main disadvantages. The first is because there's no direct linkage between the net rainfall and the base flow, we can sometimes get more flow generated within an event than actually went into the event by the rainfall. In addition, because there's no drainage of the soil moisture within an event, our percentage runoff increases throughout an event. If we've got really long events, that could then be an issue. So it's worth noting that these two disadvantages here don't really apply when we're using ReFH within our sort of standard fluvial design hydrograph development. So if you're estimating your hydrograph for a 1 in 100 year event for a recommended duration or similar, then these two issues won't actually be very important. So when we came to develop ReFH 2.3, there were two main aims. The first, we wanted to retain the simplicity of the model so that we could easily calibrate it, but we wanted to remove those two disadvantages which occur when we're using more unusual events. So the first thing that we did was look at the water balance. So here we've got a very simple event water balance. So we've got our rainfall in our event, we've got the base flow generated in the event, the net rainfall, and we've got a change in storage. If we're thinking about an impermeable catchment, then we could assume that the change in storage in an event is zero, i.e. our total rainfall in an event is said to be equal to the net rainfall, the direct runoff, plus whatever contribution there is to the base flow. Therefore, we can now estimate our BR, our base flow recharge, based on that assumption. Where the BFI host is higher than 0.5, we sort of weight that to allow some of this long-term storage to occur. And the weighting is dependent on the distance of the BFI host from 0.5. So as I said, we've also introduced a soil drainage aspect. So the model run is segmented into sub-events, each of which have got the same length as the recommended duration. An adjustment is made to the soil moisture condition for each sub-event to account for the base flow generated within that event. So that results in a slightly more complex model structure. We can see across the top, we've got our rainfall going in, it goes into our loss model. Across to the right, we've got our standard direct runoff and our routing model. We've got our base flow down the middle here, and we can see that we've got feedback into the base flow, both from the direct runoff and from the loss model. Where our event is longer than our recommended duration, there's then a feedback through back to the loss model for the next event, where we adjust our soil moisture condition. So we're going to first look at our loss model. So that's controlled by our Cmax value, and so let's have a look at our loss model. So this is our loss model. The total soil moisture capacity is Cmax. As rainfall goes into the event, some of that is run off as excess and some of that goes into the soil moisture. So we can see from this equation here, the percentage runoff, which is the ratio of the net rainfall to the total rainfall, is reliant on both the soil moisture condition for the time step before and the total depth of the soil, which is Cmax, and the amount of precipitation that goes in that time step. We now go on to our routing model, which over here we can see is controlled by our TP. So it uses the unit hydrograph method. So we've got a kink triangular unit hydrograph, which is controlled just by one parameter, this time to peak. So we can estimate the time at which the kink is just from the TP as well. So it's constrained only by one parameter. So how does the unit hydrograph method work? Well, basically, we split our rainfall event into the different time steps and estimate a unit hydrograph for each. So if our first time step, we get X amount of rainfall, we have our unit hydrograph from that event. If at time step 2, we then get another, so in this case, we've got it's scaled by about 2, so we've got twice as much within our unit hydrograph. We can then add them on sequentially. So for each time step, we then add on each unit hydrograph from that time step of rainfall. Okay, so now we're going to look at the base flow model. So this is controlled by the BL and the BR. So the base flow represents the flow in the river prior to the event, and it also shows the slow response component of the event itself. We can see here that there is an increase in the base flow throughout the event that then recesses. This is different to the FSR model where there was just a constant base flow value. So the base flow model is controlled by three parameters, K1, K2 and K3, which are estimated based on the base flow recharge and the base flow lag. So we've got our four parameters, a Cmax, TP, BL and BR. So we can say the Cmax controls the loss parameter, TP is the routing, the BL is the base flow lag, and the BR is the base flow recharge, and it's worth noting that the BR is a model state variable. So most of the time we don't have observed data, so we can't calibrate those parameters. So we estimate them based on catchment descriptors that can be obtained from the FEH web service. So TP, the time to peak, is controlled by the prop wet, which is a sign of how wet a catchment is and the sort of soil moisture deficits that build up. The DPL bar, which is an indication of both how big the catchment is and the shape of the river network within that catchment. And the DPS bar, which is the slope. So that's exactly as expected. You'd expect the time to peak to be related to how steep a catchment is and how efficient that network is as well. Cmax is estimated from both how wet the catchment is and the impermeability, which again is perfectly reasonable. BL, the base flow lag, is estimated based on prop wet, the DPL bar and BFI host, so impermeability and the size and type of river network we've got. And BR, the base flow recharge, is based on the wetness of the catchment and again the impermeability. So how well are these parameters estimated using this regionalised method? Well, here we can see the calibrated TP against the estimated TP for some of those catchments used in the calibration. So we've got TP at the top and Cmax at the bottom. Here we've got the BL and the BR. So the BL and the BR are slightly less well constrained by the models than the TP and Cmax, but the TP and Cmax are more important in defining the shape of that hydrograph. Here are the tables for the parameter estimation. So we've got England, Wales and Northern Ireland at the top, Scotland at the bottom. We can see that the difference between the catchment and the plot scale models are fairly similar, so the R squared and the standard error, there's not a huge amount of loss of performance of the model when we go from the catchment to the plot scale models. So we've estimated our main parameters. What we also need to know are these bits on the left, our initial conditions. So this is our initial soil moisture and our initial base flow. So our initial soil moisture content is the C-INI. It's a measure of how wet the catchment is at the onset of the flood event. If we're using the FEH 13 rainfall model, there's just one equation for all types of catchments, which encompasses both England, Wales and Northern Ireland and Scotland. And there is a winter and a summer C-INI value. So those initial conditions, the C-INI winter value is based on Cmax, which is the depth of the soil, and the impermeability. We then relate the summer value to the winter value, and that's based on the impermeability and the wetness of the catchment. So it's worth noting that in ReFH 2.3 there's a winter and a summer value. In ReFH 2.2 there was no summer value, however this has been retrofitted to the ReFH 2.2 model within the ReFH 2.3 software. So you can now estimate a summer C-INI value within the ReFH 2.2 model. So how do we estimate what that optimal C-INI value should be? Well, we've taken a number of the NRFA peak flow dataset catchments, we've estimated the QMED and said what's the ideal C-INI that we need in order to be able to estimate best that QMED value using our BFI host 19 and our FEH 13 rainfall model. And this is a relationship that we get with our BFI host. So that's how we've estimated C-INI value. How do we estimate our BF0, which is the initial base flow value? Well, we've got separate equations for England, Wales, Northern Ireland and Scotland, and these haven't been updated for the latest release. So having gone through the parameters that we need to describe the model and for the model to work, we also need to consider what rainfall we're going to be using. In most cases, what we're interested in is the design rainfall, and that's what I'm going to talk about here. So when we talk about design rainfall, we often talk about a DDF model, duration, depth and frequency model. So for a given return period, for example, the 1 in 100 year event that we might be interested in, for a given duration, for example, 6 hours, we can calculate the depth. We then need to distribute that across across a temporal profile. So FEH99 method uses the DDF model to produce depths for every kilometre squared. Similarly, the FEH13 provides depths for each kilometre squared for a number of different return periods and durations. ReFH2.2 has got a specific calibration for each rainfall dataset. ReFH2.3 model has only a calibration using the FEH13 rainfall. So you can find more detail about the FEH rainfall datasets in our dataset presentation. So here's a quick diagram of the FEH13 design rainfall, and you can see that we've got a number of curves for different durations and return periods. So for any given return period, we can estimate for a given duration the rainfall depth. So the FEH13 DDF model is based on annual maximum data. It's also worth noting that the T-year flood is a result of the T-year storm, and this is different to the FSR method. So 1 in 100 year flood is a result of a 1 in 100 year storm. So we can see from the DDF model that for a given return period, we also need to know what duration we're interested in. So what we often use is the recommended design duration. And this is based on this equation here, so it's related to our time to peak and our wetness, i.e. SAR. It must be an odd integer multiple of the data intervals so that we can have a peaked rainfall event. So far we've estimated our RDDF, i.e. the rainfall estimated from the FEH DDF model, but we also adjust that rainfall using an ARF and an SCF factor. So the ARF is the aerial reduction factor and the SCF is the seasonal correction factor. So the ARF reduces our point estimate of design rainfall to an estimate of a catchment average. So the idea is that if we've got a really big catchment, and we've got a small duration event, the idea of a catchment-wide storm isn't really applicable, so we reduce our rainfall to sort of replicate a catchment-wide storm. So if, for example, we've got a 1 hour duration event and our catchment is about 200 kilometres squares, we reduce that rainfall to 75%. We can see the lines here for 75%. The seasonal correction factor is required because, as I've said before, the FEH rainfall models are based on AMAX data, so we need to adjust them to account for whether we're interested in a winter or a summer event. So the research was developed as part of the ReFH research, but it's not specific to it. It relates to the DDF model, and they are generally in agreement with the results in the FSR. More detail can be found in the Kelson paper, which is in Water and the Environment. So here's some quick diagrams of the seasonal correction factor for different durations, and they show the relationship between rainfall and that SCF factor for each of these durations. So if we just look at the 1 hour event, what we can see is if we've got a low rainfall catchment, i.e. About 500 millimetres per year, then we're probably getting our annual maxima is more likely to be within our summer event, where we've got these big convective storms coming in. So for that, our summer event has got a high SCF factor. It's less likely the winter event is going to be a smaller proportion of that annual maxima. Conversely, in a wet catchment, our winter event has a much higher ratio because the probability that that annual maxima event occurs in winter is much higher. So having calculated our rainfall depth based on both our FEH DDF model, our ARF and our SCF, we then need to distribute that across time. So we use these standard profiles that have not been updated since the FSR methodology. We've got our summer profile, which is very peaky and reflecting these sort of convective storms, and then we've got a less peaky winter profile. So those are all the aspects that we need to produce our FEH2 model, and here are some of the results. So what we've got here is a comparison between the Q100 estimate in ReFH2 and ReFH2.3 against the ESS, the Enhanced Single Site Methodology, i.e. the WinFAP statistical method. We've also got the ungauged WinFAP method in there as well for comparison. What we can see is that there's little difference between the ReFH2.2 and 2.3 models. As I've said before, the differences that we've made to the water balance and the soil moisture only really occur when we're starting to use things outside these sort of standard design events. So there's little difference between them. You can also see that the performance is relatively similar to the statistical method, which means that we've got two independent methods for estimating our Q100. So here I've got a table of the performance of those different models for given catchments. We've got our bias, our root mean square error, and our FSC. What I've highlighted here is the Q2, the QMed. It's probably the only statistics that we've got a large amount of confidence in actually knowing. All the others are sort of estimates. They're compared with the enhanced single site estimate, which in itself is a model. We can see that the performances are relatively similar. ReFH2.3 and 2.2 are fairly similar in terms of the bias, slightly higher for ReFH2.3, but it also has a slightly lower FSC. The FEH statistical method has got a higher bias, but a lower FSC. And we also find that these results can be quite sensitive to which data sets you're using to develop those fit statistics. So this is the results of our rural model. What we also need is an urbanised model. So the general assumption is that we've got an urban area in our catchment. For that area, we would expect a reduction in infiltration and surface storage, so we get an increase in our runoff volume. And due to the man-made drainage structures, we would expect there to be a decrease in the catchment response time. Both of these would result in higher peak flows in our urban catchments. So if you've listened to the FEH datasets, I've gone into more detail on different ways in which we can express the urban extent within an area. So we use urban, otherwise known as urban 50K, Urbex 1990, Urbex 2000, and we can also relate these to each other using generalized equations. So it's very useful to look at those different types of urban indexes within the FEH web service. So here I've got an example of the Urbex 1990 and Urbex 2000 in Edinburgh. As I've said previously, you can't compare the two because they're both based on different land cover maps and they use different methods for estimating the index. What we can see from here is that there are some sections of development that were not present in Urbex 1990 that are now present. And bringing these maps up can also show where we've got development post-2000, which may or may not be important when we're trying to model a catchment. So in ReFH1, urbanisation was incorporated via the parameter estimation. So for example, the TP was reduced. In ReFH2, it's incorporated explicitly as per this 2013 paper. So what urban parameters do we need? Well, we've got our urban area in kilometres squared, which is the mapped urban area. By default, if no values are supplied, then the urban area is estimated based on the Urbex 2000 and the equation below. We've got our urban runoff factor, which is our IRF, which is the proportion of rainfall that results in direct runoff. By default, this is 0.7. We've got our imperviousness factor, the IF, which is the proportion of urban area which is impervious. By default in ReFH2.3, it's 6.4. It's different in ReFH2.2. We've also got our TP scaling factor, which is the factor applied to the rural TP, with the default being 0.75. We can also provide a sewer capacity and an urban area served by sewers. And what this will do will allow water up to a given capacity to be exported from the catchment. Anything above that capacity will remain within the catchment. So the routing and base flow model is different in ReFH 2.3 to previous model structures. So the first thing is that we've introduced depression storage, which you could think of as puddles. This allows us to maintain our water balance within our event. Once the depression storage is full, then we'll get runoff. The IRF is the fraction of impervious surface that is positively drained, and it's assumed to be 100% efficient. So the area of impervious surface not positively drained is 1 minus the IRF, and this is where we have depression storage. So once rainfall is in excess of that storage, it will contribute to pervious runoff. The default value is 0.5 millimetres, and this is based on both literature review and sensitivity testing of the model. So here's a depiction of what I've described there. So on the right-hand side, we've got our pervious surface. This is all within the urban area. And on the left-hand side, we've got the positively drained surface. And we can see our depression storage here. Once that depression storage is full, then it will run off and it will be added to our pervious surface runoff. So often we have a question about seasonality in urban areas. So I'm just going to run through some of the data that can allow us to decide whether seasonality is related to percentage of urban areas and what seasonality we should use. So here's a quick diagram of the ReFH residuals, i.e. the difference between the rural ReFH and our QMed observed, i.e. based on AMAX data against our Urbex 2000. We see that the bias becomes more recognisable as we get higher Urbex 2000, but it probably isn't till we get to about 0.3 that we really start to see a significant impact. This map here shows our seasonality within gauging stations. This is based on all stations within the NRFP dataset and a subset, the small catchments dataset, which also has some additional catchments as well. The direction of the arrows tells us which month of the year our highest 3 annual maxima occur within. So if the arrow is going to the east, then it's a winter event. Most of these are between sort of October and January. If it's going to the west, then it's a summer event. We see that for most of the rural catchments, most of these are to the right, and they're showing winter events. As it becomes increasingly urban, it can become more summer dominated. However, it's very difficult to sort of untangle the degree of urban and the seasonality, as most of those urban catchments are located within the sort of southeast of the country. Here's another way of illustrating this. So this is just 58 catchments where the Urbex 2000 is greater than 0.15. We can see the majority of those catchments between 0.15 and 0.3 are in winter between October and April. As the Urbex 2000 increases, and it increasingly moves to the west towards these sort of July to October events. So in observed data, what we can say is some events start to dominate above Urbex 2000 of 0.3. If you're going to use a summer event, it's important we use the summer SEF and the summer profile, and we should also use the summer CE, which is related to the winter CE. So in ReFH 2.3, it should be using a TP factor of 0.75, an IF of 0.4, and the IRF of 0.7 or 70%. It's worth noting that although the original ReFH 2.2 model didn't have a summer CE, this has been retrofitted within the ReFH 2.3 software. So if you're using the ReFH 2.2 model within the ReFH 2.3 software, you will have the option to use a summer CE value. So here's some general guidance for what you should use with urban seasonality. Most of this comes out of the small catchment work that's been completed. If the Urbex 2000 is greater than 0.3, then you should use a summer storm, and you should use an IF of 0.4 and a TP factor of 0.75. If the Urbex 2000 is less than 0.15, you should treat it as a rural catchment and use a winter storm. Guidance gets a bit more complicated when we're between 0.15 and 0.3. First of all, the catchment should by default be treated as a rural catchment with a winter storm. You can use urbanised results, but they should be used with caution or as a conservative estimate. If the urbanised results are used, an IF of 0.4 should be retained, but a TP factor of 1 should be used, as there's no evidence for enhanced routing of urban runoff. If urban results are used, a winter storm should be used for all catchments where the BFI host is less than 0.65. For catchments where the BFI host is greater than 0.65, a summer storm may be used. If you're estimating Rainfall runoff rates and storage design, it is recommended that a winter storm is used in all applications. Here we can see that final performance of the urban model. We've got our QMED from our AMAX data along the x-axis and our estimated QMED on the left. On the y-axis, and we can see that sort of a relatively not biased across the entire data set of urban catchments. So I hope that's been useful. We've got two main websites here highlighted. The first is the location of the technical documentation. There's an online wiki you can read, which will go into more detail of some of the aspects that I've discussed here. And the below reference is to where you can download the ReFH2 software from. Thank you very much for your time.